Perfect. Okay. Thank you, Shalom, for inviting me to this workshop. So today we'll be discussing how to detect generated imagery, both from deep networks as well as what we call shallow fakes. And then given that, we'll also show a deep image manipulation method that we're also very excited about. Okay, but before we begin, an important thing to note is that photo manipulation is as old as photography itself. So back in Soviet Union, if you fell out of favor with the dictator, you would just simply be erased from the photos. Now back then, it took significant expertise to do this. You almost had to be kind of a dictator to have access to these capabilities. And right now, contrast that with today, any kid in their basement can put Nicolas Cage's face simply where it doesn't belong. So AI has really kind of proliferated the ability to do image editing. Now, what we kind of see as a possible next step is to use AI for democratizing image forensics, so that you don't have to be the CIA or a major research lab in order to try to identify some of these photos. So take, for instance, this example. Was this image here doctored? Well, you see that Kim Jong-un is smiling, but it turns out in the original photo, he's not so happy, and Russian TV went ahead and just changed the facial expression that he had. Okay, now, how do you think they did this? Well, do you think they used one of these really great, really cool kind of recent deepfake methods? Well, I think it's probably very doubtful. They probably did something closer to kind of something very old school, what we call shallow fakes. For example, you can open up Adobe Photoshop right now, and there's a tool called Face Word Liquify, and this works really well. It grabs key points on a person's face and allows you to manipulate them. So there's no GAN or anything here, but it's really powerful. You can instantly cause someone to smile just with a few clicks. Okay, so if we were to try to train an AI system, how we go about this? Well, for most AI systems, we need data. We need data and labels in a supervised learning framework. Now, a problem in image forensics is that there's huge data imbalance. So there's going to be billions, maybe trillions of photos floating out there in Google, and there's going to be decidedly fewer than billions of photos that are verifiably manipulated. So what are we going to do? What we can do is we can take a little robot or a computer program and to have it generate label data for us, if we can find some sort of apparatus to do this. And turns out with this tool, we can. So the Face Word Liquify tool gives a whole bunch of sliders. For example, here you can control the eye size or the height or the tilt or the width or the distance between the eyes. And you can just randomly sample from the space and create a whole bunch of perturbations of this input face using this specific tool in Photoshop. For example, here's the original. Here's a modified version. Here's another, third, and a fourth. So the robot can just automatically generate these. And notice that it's actually not very trivial to identify if something has been manipulated. I mean, let's just show it here. So which image here is modified, the left or the right? I actually just showed you the original and the modified, and it's still kind of hard to decide, much less if you were just given an image in isolation. And we actually did this study on Turk, and Turkers got 53%. So sometimes the perturbation was just so big and it was very obvious, but this kind of indicates that this is, at a high level, a very difficult task for humans. So is it even possible for a classifier to do this task? Well, we weren't sure, but we went ahead and got a brave undergrad and tried anyways. So to do this, you can take our photos, we can Photoshop them, and then we can train a classifier to ask, is this the original or is it Photoshopped? And this can just give you a binary answer. And this would be kind of a cool detector for this one feature in Photoshop. We wanted to go even further, and we asked ourselves an even crazier question, which is, can we actually undo the Photoshop? So we can, in addition to kind of predicting a binary answer, we can predict a whole flow field and apply it to the Photoshopped image. I guess there should be an arrow from the Photoshopped image down to the warp box. And that would hopefully allow you to recover the original image. Now, it turns out this is very difficult to train, and it took a lot of hard work from the undergrad, the first author here. But it turns out you can do it if you set the right number of losses. So one thing is that you want to supervise the between the original photo and the undo. So you want a reconstruction loss in pixel space. But from there, you also need some intermediate supervision as well. So what we can do is take the original and the photoshopped, run it through PWCnet and get a flow field, and we'll call that a pseudo ground truth flow field. And then we can supervise this flow field as well. So it turns out it takes both these losses to get some sort of system that works well. Okay, let's see how it does. So here's an image. Was it manipulated or not? We can ask our binary classifier. It turns out it was. From there, we can predict the flow field, and here's a heat map of the flow magnitude visualized. So we see that the system is predicting that the eyes were touched and the lips were touched. And if we apply the flow field, we can see that this is the suggested undo. And so you might have caught it, the lips and the eyes kind of moved a bit. It turns out this is the original, and I can flip between the manipulated and the original, and you see that there's a big perturbation. Whereas between our undo and original, it's much smaller. And this indicates that our system was able to successfully undo it to some degree. So here's another example. Here's a manipulated image. Here's its flow prediction, rather large on the cheeks. Here's the suggested undo. And here's the original. And here I'm showing the manipulated and original. It's kind of a large glaring change. And the undo and original. It's much smaller. Okay, so we need to somehow evaluate how well our system is doing. The first thing we can do is on a validation set, also with the random warps, just see if we're fitting our training distribution at all. And we can check our binary classifier, and it turns out it's doing quite well. It's at 97% raw accuracy and 99.8% average precision. Okay, so this indicates that this training distribution, which was actually very difficult to fit if you trust the Turk data, a computer can actually go in and find the right set of cues to solve the task. We can also evaluate the undo. And so here I'm going to show the PSNR. And this is before means the PSNR between the manipulated image and the original. And that I'm going to show on the bottom. That's at 31.4 PSNR. If we take the flow field, so this is if you have access to the original and the manipulated, compute the flow field and warp the manipulated image back, you get 40.2. And the reason this isn't infinite is because there may be small errors when you're predicting the flow, and when you warp an image, you're going to have to lose information because you're going to be compressing certain pixels. So it's not going to be infinite, but you get something really, really high. So can our system actually bridge the gap between these two? And turns out it can to some degree. It's able to make up about a third of the ground and get up to PSNR 34. So it's not perfect. This is a really difficult task. If I gave it to you as a person, you probably wouldn't be able to do it, I would think. But the computer is able to reverse it to some degree. Now, there is one big problem here, which is that we did a whole bunch of random warps at training time. Will that actually generalize to real life use cases? And that's a question that we really wanted to ask. So we hired an artist to use this feature in Photoshop to manipulate a small set of images. Now note that this costs resources and time and money. There's no way we can hire an artist or 1,000 artists to generate a whole training set for us. That's going to be prohibitively expensive, but it is cheap enough to and easy enough to do just for a hello test set to see if the system that we built is any good at all. Okay, and if we look at our binary classifier, it goes down to 90 and the AP is 97.4. So there's a drop off between the random warps and the artist generated content, but notice that this is way above chance. This is way above 50% or the 53% Turk test, which indicates that we indeed got some generalization. And if we run the same test on our reversal, we see that we're able to make up the ground, less ground than before. But again, we got some generalization. And so this is actually kind of exciting to me because on the left, the training data was collected for free. We kind of made up this training process and it projected, pretty positively onto a distribution that we actually care about. Okay, so one important thing in forensics is how robust you are to downstream corruptions, because oftentimes you're not just going to get the image in the PNG. It's going to maybe be blurred or resized, or JPEG. And so here I'm showing the performance of the binary classifier as you apply perturbation. So on the x-axis, we're applying more and more blur, more and more Gaussian blur. And on the y-axis, we're showing accuracy. And here we see that if you train without augmentations, you quickly drop down from nearly perfect to nearly chance. That's the yellow. And the green shows that we're a little bit more robust if we train with the augmentation. And here we do the same thing with JPEG. Okay, now we tried an even kind of crazier perturbation, which is we did what's called print rebroadcasting, which is we printed the image out and then I rescanned it in. So I did this manually for a few hundred images when I was at work, when we had access to free printing. Okay, and this is what we got. So before printing, you see that the yellow is very high. That's without augmentation. But after printing, the yellow drops down by a bunch, whereas the green, which is trained with augmentation, is more robust. And I think this is interesting because the perturbations on the left, like blurring and JPEG, it's easy to train with those in the loop. And really, we should be all be doing that. It's just, you know, it's a PyTorch function. It's so easy now. But the perturbation on the right, you cannot train with, right? I'm not going to be sitting there printing images and rescanning them. It's really hard to simulate as well. Okay, here's an example on an artist-generated example. So what they did here was actually a little bit more than warping. We actually, for part of the set, also for a few examples, we also said that they could do other types of retouching, such as kind of photometric changes. And so we see that this is a manipulated image. This is the flow prediction. This is the suggested undo, which I think looks much more natural, and the original photo. Here's the manipulated and original, where you see large changes, and the undo and original. Okay, so we've looked at a few sets of generalization, for example, different post-processing, such as print rebroadcasting, as well as looking at the held out set that's generated by an artist. And from here, we were a little bit puzzled. How is the system even doing this task? Like when I look at the image, I really, a lot of times don't have any clue, at least on the training distribution. So we wanted to study this a bit further. And to do that, we looked at what types of images it could generalize to. For example, different types of images that you can warp and different image domains. Sorry, the first is different types of warps. So we're going to take faces here. We trained on Photoshop. Let's see if it generalizes to Snapchat. Okay, so here's a Snapchat manipulation. It's actually not that hard to tell that this has been touched by Snapchat. There's this very signature Snapchat look that some find fun, I guess. And we can see that our system is actually able to pick up on these very exaggerated changes that actually weren't in the training set, because Photoshop actually doesn't go this far, I think. Okay, and here's the undo. It makes the eye smaller, you can see. And here's the original. So our undo, I think, didn't quite get far enough, but it was in the right direction. So there's some generalization across warp methods. So we're testing on a face with a different type of warp, and it still works. What if we don't test on a face at all? So here's an image of a flower. We can apply a warp from a face, just so the warp is in distribution, but the image is not. And here's the result. And if we apply our system, this is supposed to be a heat map overlaid, but there's nothing. It totally fails. It just is not successful at all. And so it doesn't generalize well to any arbitrary image, but it did generalize to warped faces from Snapchat. And so this indicates that there's some specialization to the face domain. It's picking up on perhaps parts of faces or something, some distribution of arrangement of face parts. Now we can go actually very far and actually try a completely different type of image. And this is just white Gaussian noise, right? This is not in our training distribution at all. We could try this as well. So we apply a warp that belongs to a face, and there it is. So it's going to compress some pixels and stretch some white noise pixels out. And if we run this through our system, even though it's never trained on white noise, interestingly, it can pick this up actually pretty easily. So how and why is it doing this? Well, if we do some introspection, when Photoshop is warping an image, it's compressing some pixels at certain regions and stretching other pixels out. And when you're stretching pixels, you have to interpolate, essentially make up data. And the system seems to be able to pick up on some of these cues, okay? So it seems like it's able to pick up on different cues from both high level and low level, which is, I think, kind of interesting. Okay, so what we've seen here is that if you're given a relatively static tool, it does pay to just directly specialize for it. Like Photoshop there are a few major releases a year. So if you train a Photoshop detector button, there's going to be maybe millions of users that are using it. So it's going to be relevant for a long time. The representation we learned seems to pick up on both low and high level cues as well. And the data augmentation helps generalization, for example, if you're doing print rebroadcasting. Okay, now we do still care about deepfakes because perhaps this is a problem that will be of greater concern in the future. For example, deepfakes and GANs are making fake imagery easier and easier. And here we're asking, can we possibly create a universal detector to grab these? To study this, we got a data set of CNN-generated fakes from all sorts of different types of generators. Now, if we were to take the previous approach, we would specialize. We would train one detector for every single one of these, and it would be able to catch that specific algorithm just fine. But we don't actually know how well it'll generalize to future algorithms. So what we might want to do if we wanted to perfectly generalize as well as possible would be to train on all this data and then test on the future algorithm. Now, to study this, I don't actually have tomorrow's algorithm today. So to make kind of a more scientific test, we wanted to see how well it would do if you just train on one and generalize to the other. Now, this may very well fail because there are many differences, for example, in architecture, data sets, and objectives, and generalization is just difficult. I mean, that's why domain adaptation is hard. But the optimist in me is saying that perhaps there's some underlying commonalities that can help enable generalization. And that's what we study here. So the methodology is very simple. We take a GAN, generate images, then we train a classifier between the real and the fake. Now, this might look familiar to you. It's exactly how a GAN is trained, but there's a key difference, which is the generator is fixed. And that means that the discriminator can be trained to convergence, so it can be as deep as you want and train for as long as you want. And you don't have to worry about any sort of mini-max training dynamics here. So that's the big difference between this and, again, the generator is frozen. From there, we can freeze the classifier, F, and try to see if it can grab synthesized images or if it can tell or detect synthesized images from other CNNs. So we're going to show those results here. On the y-axis, I show average precision, where the bottom is chance and the top is perfect. On the training distribution, if you train and test on ProGAN, even if it's on different sized images, it's trivial, you get 100%. Now, if we look at all the other methods, we're doing above chance, which is encouraging, but the performance is rather inconsistent. You see, we have 100s, 98s, 94s, but we also have some 60s and 70s. Okay. Now, what we found is that, again, if you do heavy data augmentation, something interesting happens. We tried a whole bunch of other methods I should mention, but this data augmentation result we ran out, we were actually very surprised when we saw these numbers. So one thing to note is that augmentation is not always appropriate. For example, for deepfakes or super resolution, you're looking for very kind of low-level, high-frequency cues. And if you do blur and JPEG data augmentation at training time, you're kind of wiping away the signal. So it's just not appropriate to do it there. But for other types of CNNs, we add surprising generalization. So everything here is almost in the 90s. And this really surprised us because we tried a whole bunch of things that were much more complicated, and turns out just turning up the blur in the training augmentation really helped. Okay, now why is this? Well, we did a little bit of a study back in the training distribution. So the training distribution at first glance isn't that interesting. It's 100% whether you do augmentation or not. And note that all these bars here at test time have no augmentation. So they're just the clean image that come out. But we can also add blurring at test time and see how performance degrades. And that's what I'm showing here. So as you're adding more blurring or going to the right, performance is going to decrease from 100% perfect down to 50, which is chance. And you see that happen quite quickly with the yellow curve, which is trained without augmentation. Now, if you recall from our Photoshop experiments, when you train with augmentation, the curve usually goes up, and that's what we expected here. But we see that it doesn't only go up, it goes all the way up to 100%. like it cannot do any better. It's straight up at 100%. And this is actually really interesting because it indicates that there are actually cues that tell whether something is program generated or real at a whole bunch of frequency bands. So when we first think about GAN artifacts, we're thinking about like checkerboard artifacts or just really small things that the GAN or generator just can't get right in the end. But it turns out that even if you remove that information by blurring, you still have other cues at all the other frequencies, the mid to low frequencies, that can give the image away. And actually, by forcing the classifier to pay attention to those cues, you end up getting a more robust classifier that generalizes better to other distributions. So if you only care about ProGAN, you wouldn't really care about which frequency band of cues you're looking at. But it turns out the mid and low frequency bands generalize better to other networks such as Big GAN and Style GAN and such. And so this was kind of a surprising finding to us. Okay, so what this study suggested is that CNN generated images do have common artifacts. And it turns out those artifacts can be detected just by a simple classifier. And in fact, we did this study and released it on arXiv. And just a few weeks later, StyleGAN 2 came out. It was released after our submission, and we ran it out of the box. And on FFHQ, it got a really good score. It got 100% average precision. And what's interesting this week is that there's a new paper from MIT, from Lucy Chai et al., that indicates that maybe this is not just specific to CNNs, it may actually generalize beyond CNN. So I'd encourage you to look at this study for a whole bunch of neat experiments. Now, I do want to exercise some caution here. So note that what we're reporting on is average precision. So average precision, if you get 100%, it means that if you you run all the images, you get all the logits, and you sort them, it indicates that the generated images are completely separated from the real images. That is, they're basically sorted in the right order. But that's actually very different than making a real fake decision on a per image basis, where you need an accurate threshold. And so that's actually much more difficult. Also, this situation here may not persist. So GANs themselves are trained with a discriminator, and we explored this connection before. It turns out that they don't reach the Nash equilibrium right now, but perhaps someday they will reach the Nash equilibrium with a discriminator that's infinitely large. And if that happens, then even if you freeze the generator after the fact, the discriminator won't be able to pick up anything. The game will be over. So if we actually reach that point, this phenomenon may not hold any longer. And this study, at least this study, just focused on CNNs. I think it is possible that at some point there's some big future architectural changes that might throw off some of these conclusions. So that also remains to be seen. Okay, between these two papers, I think what we see is that forensics in general, there's maybe a multi-pronged approach that is beneficial. So for rapidly evolving tools, such as for generative models, where there's something new appearing on arXiv and ECCV just all the time, we want a system that's able to kind of continuously train on more and more of these methods. And we're really relying on generalization to catch the next method that comes out, because you might see the fake before you get kind of a verified fake to train on. But for relatively static tools, it does pay to specialize. And in some scenarios, you're actually kind of have a combination of these two. But these are kind of two endpoints that you can think about these approaches in. Now, detection itself is only a piece of the puzzle. So I'll also encourage you to look at the Content Authenticity Initiative, for example, which is a collaboration between Adobe, the New York Times, and Twitter, which is looking at establishing a kind of open source format for provenance. And so there's a white paper that I'll refer you to on this website. And lastly, forensics is important because we'd like to detect pieces of media if they're intended to deceive. But a lot of these synthesis and manipulation algorithms, their intended use is really not nefarious. It's for creative uses. And so here's an algorithm that we're actually quite excited about. And so this is recently on arXiv, which is called Swapping Autoencoder for Deep Image Manipulation. Okay, so here we'd like to learn in an unsupervised way on a collection of of images. So here I'm just going to show churches as a running example, but later we'll show images on faces as well, because this is a kind of synthesizing humans workshop. Okay, so our goal here is that we'd like a representation that's amenable to downstream manipulation. And we'd like it to be very flexible. So we don't want to consider any individual manipulation. We'd really like it to be easily usable for a whole bunch of possible ones. For example, you may want to, given an image of a church, you may want to edit the structure. You may want to try to change the global style of the image, or kind of the time of day of it, or things related to that. One thing that we like to do for GANs, for example, is to perform image manipulations or kind of image morphing. And something very similar to that is vector arithmetic. If you can find directions in the code space that make kind of sense and are interesting. But first and foremost, the most important property is that the image should be recoverable from the code. Because if it's not, if your representation cannot recover your original input image, you're not actually editing your input image, you're editing some other image, okay? And so this is first and foremost. And notice that nowhere did we ever say that we wanted random sampling. So GANs are really great for learning image distributions on unlabeled collections, and they rely on random sampling, but we don't actually need the random sampling. What we'd really prefer to have is be able to find our image. And that's actually somewhat of a challenge when you train a GAN. Okay, so we're going to instead take an autoencoder-based approach, which is you're given an image and you want it back. And we can enforce that with a reconstruction loss, and we want it to look realistic at all. And now we'd like this code in the middle to be useful. So our hypothesis is that if we divide it into something that corresponds to structure and style, and I'll put those in quotes because we'll kind of get more concrete definitions later. Our hypothesis is that that code will be amenable to manipulations later. Now, how do we get these codes to actually do these things? Well, we use this tool called swapping, which has also been explored in some cool recent works. And the idea here is that we'll use a second image, in this case, St. Basil's Cathedral. We'll grab its vector or style code and decode that with the structure code from Notre Dame, and hopefully see something like this that grabs the structure from one image and the texture or kind of the textures from the bottom image. Okay, so here we're using swapping as a pretext task, so it is cool to be able to do this exact task, but our goal is to see if this pretext task induces a useful representation downstream. Now, how in the world do we actually define and enforce style? Okay, so we're going to explore that next. And really, we're actually very inspired by classic work in texture analysis by Jülich. Okay, so Jülich back in the 60s was really trying to think, what are the sufficient statistics that that describe whether two patches belong to the same texture or not? And this is actually a very difficult question to find these statistics. But we're inspired by this approach, and it turns out we can use some kind of modern tools to find those statistics for us. So given an image, we can take two random patches, and we can use a ConvNet to try to extract the relevant statistics in the front end, and an MLP that takes the patch statistics and asks, are they from the same or different image? So you can think of the front end as finding the relevant features for this task, and the back end as building kind of a co-occurrence model over whatever features are relevant for determining patch co-occurrences. So let's try this. Let's play a game together. So here are two patches. Do you think they're from the same image or from two different images? I guess if we were live, I would ask for immediate feedback, but I'm going to guess that you think that these are from two different images, and you would be correct. How about these two? I think they're from the same, and indeed they are. How about these? Different again. And how about these? Same. Oh, wait, look at this. Maybe I hopefully tricked you a bit, and they're from two different images. And in fact, this is our result. If we take this structure image on the upper right and stylize it with the image on the left, we get this result here on the right. And so here, we're going to essentially define this token, this word style, as saying if the images have the same co-occurrence statistics over relevant patch features, in some sense, they share the same style. And that's actually how we implement this loss. And there's a bit more to it. Instead of just using 2 patches, we actually use a few random patches from the bottom image. And that's just to get kind of a distribution over the textures that are in that image. And then we can judge a single patch from the output to see, does that belong or not? And so that's how we enforce this bottom branch. We call it a patch co-occurrence discriminator. So it's a discriminator that's conditioned on orderless random patches from the reference image. Okay, let's see some results. So if we take this Notre Dame and we stylize it by itself, it's an autoencoding result, so you get the same image back. But here with a different image, it's something interesting. And we see different results here that really show that it's, so at first glance, maybe you think it's just doing like color histogram matching, but it's actually doing more than that. You can see that it's actually constructing some of these towers that we point out with these red arrows. You can run this exact same algorithm on different data sets, for example, a bedroom. And this isn't perfect, but you see in general, the sheets transfer the sheets, the walls transfer the walls, etc. And here's some landscape photos. So you see that vegetation can transfer along with clouds, as well as this desert pattern. And finally, we can run this on FFH2 as well, and we can get this kind of mixing effect that you also see in generative models, for example, with StyleGAN. Right? So we're grabbing the structure from one image and the kind of feel or the style from the top row. Okay, so here we kind of just asserted that co-occurrence patch statistics were a good representation of style. We actually should do some comparison, and we do this. So here's our result for stylizing this church. Here's a result with the generative model. And as I mentioned before, a tricky part with generative models is that if you just do style mixing with randomly generated images, the results look great. But with a specific image, you have to find the image. And when you find the code, it might actually ruin the downstream mixing. And so that's why these results don't look as good as the mixing results you may see with randomly generated images. Okay, we can also compare to photorealistic stylization methods like STROTS and WCT2. We ran a Turk study that said, which one do you think is more similar, ours or a baseline? And this was, of course, blind, and we randomized the order. So we asked them to choose left or right, where they don't know if ours is on the left or ours is on the right. But in this study, our method is chosen more often than the generative models, as well as the photorealistic style transfer methods. Okay, so we've seen that we can directly do photorealistic stylization, but we also want to see if we can do other types of manipulations as well for free. Does the representation give us these capabilities for free? Okay, so we're going to actually try this. So here we're directly editing the structure code. So we're going to take this point in the sky and try to overwrite a point in the mountain. So we change the mountain to a sky by editing the structure code. And we can also take a whole bunch of images in the training set, encode them in the space, and run PCA to find interesting directions to walk in. And we show those directions on the right, and we see that a user can come in and change that. And so putting it all together, let me just show you this very cool UI that Taesung developed. So here you can first change the kind of global feel or style of the image by adding vegetation or making these more barren. Here you can see that at some point mountains will grow in the back. And we can directly edit the structure code by erasing mountains or adding mountains as well. And we can also add a bit of water here on the bottom. So this is just a kind of fun UI to play with. Okay, and we can also do this on faces as promised. So here are some directions that were found using that UI. So Taesung went through and kind of manually selected interesting axes. So for example, this one corresponds to days, it seems. Here we're playing with the eye size. Here, this element can kind of play with the nose. And we can also do kind of bigger changes like lighting, relighting. And keep in mind, these are all real input images. They're not randomly generated images. Okay, so here's just some individual examples across different manipulations. And lastly, one fun aspect of this is that even though we're training without labels, so we're training in this unsupervised way, asking for the system to disentangle style and structure. After the fact, you can actually sprinkle in labels if you have them and define some sort of new task on the fly. So for example, here we're training on a data set that's with a bunch of paintings and with a bunch of images kind of concatenated. And at training time, it has no notion of labels at all. But at test time, you can find the direction that walks from paintings to real images. And you can apply that to the paintings. And that's what we get here. So I'll kind of morph between these two. Okay. So this system, we're looking at doing unsupervised style and structure disentanglement. And really, we kind of proposed this loss here, this patchwise co-occurrence discriminator, and it seems to correlate really well with what people would call style. It supports a whole bunch of downstream manipulation tasks that we explore with the UI. And one thing is that it's detectable because it uses a CNN. So we actually, I mean, we did this project way after Shengyu did the synthesis project, but we ran that classifier and got 95% AP. So it's kind of interesting to note that that result kind of continually holds as we develop new methods. Okay, here are my co-authors. I'd like to point out especially Shengyu and Taesung, who are the first authors on these papers that we talked about. Okay, thank you very much.
Thank you. Thank you for the talk. Again, if you have questions, you can press the QA button and then ask. So I have a few questions here. So in the first work, you kind of show some cross software generalization, like training on Photoshop and then try to use Slapjack and then see it still works. But the problem of Slapjack example is that this is just the changes is a large amount of changes on the faces. The eye is enlarged a lot. So it's kind of easy to spot. But what if we are using a lot of software to still make the face look very, very realistic, and then can it correct back? Yeah.
It ends up depending. So there's another tool in Photoshop called Liquify. So basically where Liquify grabs points on your face, and so kind of constrains the warps you can do. Liquify allows you to just warp, kind of define your own flow field. So it doesn't generalize as well to that, but it generalizes pretty well to Facetune. So at some point, someone took our software and made an app, and I think they started charging like $4, but they ran it on Facetune results, and it's generalized to that. So maybe it's kind of constrained to warps. So warps that are kind of face aware, it kind of does well on, and then arbitrary warps, for example, on flowers, or if you just randomly warp your face, it doesn't generalize as well too, it seems.
So does it make sense to train with data from multiple sources? So data collect from Photoshop and other software and then train together.
Yeah, and I would say it may actually make sense to train individual classifiers in those cases, because there are millions of Photoshop users, there are millions of Snapchat users, millions of Facetune users. And whenever you kind of constrain the domain, the classifier may have an easier time. You can kind of have a suite of these tools.
Okay. Another question is, you mentioned this in the last word, there's this disentanglement of style and structure. So the texture co-occurrence backward thing you introduced. So did you see like there's an obvious difference like with and without this texture co-occurrence backward?
Yeah. So one thing we did was there's a knob you can turn actually with this patch co-occurrence system, which is the patch size that you use. And so if you use, for example, really small patch sizes, like 1 by 1 patches, then you're literally doing color distribution matching. And if you make the patches go up, then you're actually, that texture has more kind of style or structure components. And we actually we kind of turn this knob and we can trace out that you can actually trade off between style and content by turning this knob. So it does have an effect for sure.
But if you completely turn this thing off, like just using this spatial feature to represent structure and then the FC feature to represent style, and then do this autoencoder training,
Yeah.
does it generate reasonable results?
Yeah, we may or may not have tried it at some point. I should definitely look back. Yeah, so one thing we didn't mention was the style and structure. There's an inductive bias in the code design. Like one is kind of a vector and one is almost a matrix. It's like a very skinny tensor. So that already, yes, you're right. That already gives you something. But what we like here is that by putting in the loss, you have some sort of better definition of what that vector exactly should be doing. Yeah, but you're right. Yeah, without it, it does do something reasonable.
I see. So there are some experiments on the style transfer results, but normally when I see style transfer papers, they are all rendering very, very beautiful results. So do you see in generally you are better than style transfer, and then or there are cases style transfer is better, and it's hard to say.
Yeah, so one thing that we have going for us is we trained on, like we just trained on churches, for example. We have a network that's just trained on churches. I mean, this is what StyleGAN does too. They kind of limit the domain. And when you're within a domain, you can do really well. And so that is one advantage that we have. Whereas, for example, like WCG2 is trying to do a whole bunch, like a wider range of images. Whereas here we're training, kind of one network for one kind of class. Yeah.
Okay, so there's one question from the audience. The question is, can the first method, the flow-based legwork for GAN manipulated, work for the GAN manipulated images? For example, the eye gaze image change shown in the last paper.
Got it. Okay, I'm pretty sure that failed. I know the other direction failed. Like we tried taking the program generated classifier and running it on Photoshop, and that one failed. And I'm pretty sure it would fail in the other direction too. I don't quite remember we did that experiment, but yeah, that's an interesting question.
Okay. All right. Are there any more questions? Okay. If they are not, then that's it. Thank you.